Hey y'all, what's up? We are gonna do a center of mass question here where we use a double integral to find the center of mass of something. Now, before we go into the actual problem, I want to explain a little bit of the shortcomings of this type of problem in that it's like it only has a certain sense of reality. Um, we have a flat plate here that only has x dimensions and y dimensions. And I can find its center of mass, and as you can imagine, its center of mass has an x bar and a y bar. So an x center of mass and a y center of mass. If I want to do a three-dimensional, say I had like a rock, right, and I wanted to find the center of mass of some weirdly shaped rock, right? I would need to do a triple integral to find that. So we need to do this first in 2 dimensions before we bump it up to 3. So we have a flat plate that is in the shape of this parabola, 1 minus x squared. It has a density function. We have a delta here, Greek letter, of y. So that means that the density gets bigger as we go up here. Added this because we should really talk about units. If x and y, for example, were measured in centimeters, and the density was measured in grams per centimeter squared, and that is like the two-dimensional density as opposed to a three-dimensional density and something like this, then what would the mass be measured in? Well, it would be measured in grams. Why is that? If you look at this, this would be my grams. This dA would be a area unit with centimeters, so it'd be centimeters squared. And notice when I multiply centimeters squared by grams per centimeter squared, I get out centimeters. And that area gets multiplied when I do my integral. So hopefully you understand the setup of this problem. We are going to do this in 2 parts to find the center of mass. First thing I have to do is find the mass. And the second thing I need to find is the center of mass. And I left something out. Mass is always the double integral over r of density dA. X bar is 1 over the mass times the double integral over r of x times the density dA. And then this one should be a y times the density dA. And sometimes we have shortcuts. I'm going to actually try to demonstrate that with this one right here. So let's start by finding the mass of this thing. So I need to set up my bounds. I'm going to use the same bounds all the way through. R, you can see with this one, it's easiest to go from left to right on the x's, -1 to 1. And then on the y's, I'm going to go from 0 up to that parabola. So when I build that region out, my mass is equal to the double integral over r of density dA, which that's going to be the integral. I got to have -1 to 1. And then I'm going to need to have 0 up to 1 minus x squared. My density is y. And then how's the dA going to work? Well, I'm going to go dy, and then I'm going to go dx. There's a couple ways to check that. Remember, if I have a dx here, then the last bit of the equation should have x's in it. And you should see when I integrate and I plug in these bounds, I'm going to get x's. So, another shortcut I'm going to take here, or a shortcut that I'm going to take here, is the density is only dependent on the height. So I think you could easily argue that this right half, because it has the same symmetric shape as this left half over here, is going to have the same mass. And what I can do is say, instead of doing the integral from -1 to 1, and then this to this of this, why don't I just do the right half and double it? And that's totally legitimate. And we can work it out mathematically, and I'll do that in a little bit as well. So I'm going to do 2 times the integral from 0 to 1, and then the integral from 0 to 1 minus x squared of y dy dx. Anytime I have zeros in my integration, it's going to be easier. Well, most times. All right, so let's do this integral. All right, I'm going to get 2 integrals 0 to 1. All right, when I integrate y with respect to y, because that's my inner integral, I'm going to get 1/2 y squared. And then I'm going to evaluate that from y equals 0 to y equals 1 minus x squared. And then I need to put my dx there. So one thing that is pretty convenient here is that and that cancel with each other. So I get the integral from 0 to 1. And look, when I plug these bounds in, I'm going to get 1 minus x squared. That's the upper bound here plugged into this without the half. And then when I plug in the 0, I'm going to subtract 0. So I'm not even going to write that piece. Actually, maybe I will, so you can make sure you see it with a dx there. From there, I need to square that piece out right there. If I had something like an x right here, which I'd look for if it's possible, then I would have some u sub there. But I don't, unfortunately, so I have to FOIL this out. This is the integral from 0 to 1. I'm going to have a 1. My middle term is going to be 1 minus x squared times 1 minus x squared multiplied by each other. You should see that my middle term is going to be a minus 2x squared because there will be 2 of them added. And then I get plus x to the 4th dx. And then this I can use some simple power rule with. That gives me integral 0 to 1. Or sorry, I don't have to do that anymore because I'm going to integrate it. All right, I get x minus 2/3 x cubed plus 1/5 x to the 5th evaluated from 0 to 1. From there, I can, again, this is why it's nice to have this 0 here, because 0 plugged into all these pieces is just going to give me 0. And this 1, when I plug into all those pieces, is just going to give me the coefficients of all these things. So when I evaluate that thing, I'm going to get 1 minus 2/3 plus 1/5. You should be able to do a common denominator. It's going to be 15 is my denominator. So 15 2 gets multiplied by 5 minus 10. The 1 gets multiplied by 3 plus 3. So when I do my arithmetic there, I get 8 out of 15. If we were using units, which I didn't really specify them, I just sort of said if when I drew this green stuff up here, that would be grams. So that's the mass. Now to do x bar. So with x bar, you could do the math out. We could do all this double integral density x, but I sort of already made an argument for what the center mass, the x center mass should be. It should be 0. And let me explain why. We just said that this right half, because of symmetry and because the density is only dependent on the height, is going to be the same as this left half. Well, what's that mean in terms of center of mass? Well, if the two halves are equal, then the center of mass is right in the middle of them. So that x bar is going to be 0. You can say that the center of mass is 0 because of symmetry. You can say I think symmetry is the best way to say it, because this is totally symmetric left and right. If you recognize that, then it can cut the amount of work down, right? So I'm going to come down here and write x bar is 0 because of symmetry. Oops. And for y bar, it's going to take a little bit more work, and so I'm going to do that in the next video, and we'll pick up right where we left off. I'm going to do this work right here, so I'll see you in a moment.